All right, today we're going to dive into one of the most fundamental and I think one of the most beautiful techniques in all of chemistry, recrystallization. It's really this art of taking molecular chaos and turning it into perfect, ordered purity. So just picture this. You've just made a new compound in the lab. It's super promising, but let's be honest, it's a mess. It's all mixed up with all sorts of unwanted gunk. So the big question is, how do you clean it up? How do you get from that crude, clumpy powder to a vial of sparkling, absolutely perfect crystals? Well, that's exactly what we're going to break down. And you can see the difference right here. On the left, that's your starting point. It's often discolored, it's structurally messy, and you really can't rely on it for anything. But on the right, that's the goal. A bright, pure, highly ordered substance that's ready to go. I mean, in medicine, purity can literally be the difference between a cure and a contaminant. For new materials, it's the key to making them work at all. It all comes down to purity. And that brings us right to the heart of the matter, the purification problem. Because in chemistry, purity isn't just about making things look nice. It is absolutely mission critical. You see, impurities can totally change a substance's properties, making it useless or even dangerous. So what are we actually trying to get rid of here? Well, these impurities fall into a few main camps. You've got stuff that's less soluble than your product, some stuff that's more soluble, and then you have these sticky, resinous materials, and they're usually the culprits behind that dark, ugly color. You gotta know your enemy to defeat it, right? Each one needs a slightly different strategy. So how do we tackle this? Well, enter recrystallization. It is such an elegant solution. The core idea is incredibly simple, but wow, is it powerful. We're basically going to use temperature to convince our desired compound to separate itself out from all that other junk. Honestly, if you remember just one thing from all of this, make it this sentence. Dissolve hot, crystallize cold. That is the mantra of recrystallization. It all works because we're exploiting a simple fact. The solubility of most solids goes way, way up as you increase the temperature. Okay, so here's the game plan, broken down into 4 key steps. First, you dissolve your crude stuff in the absolute minimum amount of a hot solvent. Now, if there's anything left that didn't dissolve, those are your less soluble impurities. You just filter them out while everything's still hot. And then, here comes the magic. You let it cool down nice and slow. As it cools, your pure compound starts to crystallize out. And finally, you just filter off those beautiful new crystals and let them dry. So, what's actually happening on the molecular level? Oh, this is the cool part. As the solution cools, it gets super saturated. The molecules of your good stuff start finding each other, and they lock together into this perfect repeating pattern, a crystal lattice. And this process is super selective. It's like a VIP club. The impurity molecules, they don't have the right shape, they don't fit the pattern, so they just get left out, stuck floating around in the cold solvent. But here's the thing. This entire beautiful process hinges on one single critical choice. We absolutely cannot talk about recrystallization without focusing on your most important tool, the solvent. Your success or failure, it all comes down to picking the right one. And this quote just says it all, doesn't it? Choosing the solvent, and just as important, the amount you use is this incredibly delicate balancing act. Use too much and your product will just stay dissolved. Even when it's cold, poof, your yield is gone. Use too little and you'll trap impurities right inside your crystals as they form. It has to be just right. So what makes a good solvent? It really comes down to 2 golden rules. First, your compound should barely dissolve in it when it's cold. That's crucial so your product will actually crash out of the solution when you cool it down. And second, it has to be super soluble when the solvent is hot. That's what lets you dissolve it in the first place. Now here's a key number, a real pro-level detail for you. You want the solvent's boiling point to be at least 15 to 20 degrees Celsius below the melting point of your compound. Why? Well, if your substance melts into a goo in the hot solvent before it actually dissolves, it can separate out as an oil instead of forming crystals. We call this oiling out, and trust me, it is a purification disaster, a total nightmare to fix. All right, so you've got the theory down. Let's get into some practical pro-level tips for when things don't go quite right. Think of this as your troubleshooting guide to getting those perfect, sparkling crystals every single time. This happens all the time, and it's probably the most frustrating problem. You've cooled your solution down, you're waiting and waiting, and nothing. The solution just sits there perfectly clear in a stubborn, supersaturated state. What do you do? First of all, don't panic. You've got a few tricks up your sleeve. You can seed it by dropping in one tiny, perfect crystal of the pure stuff. That gives the other molecules a blueprint to start building on. Or you can scratch the inside of the flask with a glass rod. Those tiny, microscopic scratches on the glass give the crystals a place to start growing. And you know what? Sometimes the best tool you have is just patience. It can take hours, sometimes even days. Okay, on to the next problem. You've dissolved your crude solid, but the whole solution is this nasty, dark color. It's probably from those resinous impurities we talked about. So how do you clean that up before you let it cool? Oh, the solution for this is so simple and so cool. Activated carbon. You just add a tiny bit, like a small spoonful, to your hot solution. This stuff has a massive surface area, and it's incredible at grabbing onto those big colored impurity molecules. It basically acts like a molecular sponge. You then filter the carbon out, and voila, your solution is suddenly crystal clear and ready to go. Now, something that's really important to get is that you almost never get 100% of your product back on the first try. A pretty big chunk of it, maybe 20%, often stays dissolved in that cold solvent. We call that leftover solution the mother liquor, and this is why a cardinal rule in the lab is you never throw out your mother liquor right away. You can often boil off some of the solvent and get a whole second crop of crystals from it. This chart really just drives home the whole principle, doesn't it? We are looking for a solvent that has this massive difference in solubility between cold and hot. That steep temperature gradient, that huge jump on the chart, that's the engine that powers this entire purification. The bigger that difference, the better your recrystallization is going to be. And here's one last crucial pro tip for you. Don't just get the solvent warm, get it to a gentle boil. For most things, that solubility curve we just saw is steepest right near the boiling point. So heating it all the way to boiling, make sure you're dissolving your compound in the absolute minimum amount of solvent, and that directly translates into the maximum possible yield of pure crystals when you cool it down. So let's just recap this journey for a second. We started with a crude, messy, impure solid. Total chaos. And just by applying a simple principle of temperature and solubility, we've systematically kicked out all the impurities and just let nature do its thing, building a perfect, ordered crystal lattice. It really is a beautiful process of turning chaos into order. But you know, when you step back, this technique is more than just a procedure in a lab. It's a really powerful metaphor. This quest to isolate one single pure thing from a complex, messy mixture is just fundamental to science. So it makes you wonder, right? Where else in our world, in technology, in the data we use, maybe even in our own ideas, is this relentless drive for purity a critical force for innovation and progress? Something to think about.